Hello everyone, in this video I will show how to simulate a PWM using C++ in QSPICE. Therefore, I set everything up already, just the inputs and outputs for the C++ block in QSPICE. The duty cycle is one input, and this is the one we want to put out in the PWM. The input port is an integer. And the duty cycle goes up from 0 to 100 and then down again to 0. The other input signal are the ticks shown here. And I use ticks of 1 megahertz, you can see. And they are 1 megahertz ticks. And this will be our time base for the counter in the PWM. The ticks are a Boolean input, and the PWM are a Boolean output. Now let's continue with the programming of the PWM. Therefore, I will open the PWM block, right-click, C++ interface, and open the C++ source. Previously, I just generated this template, but there's nothing in addition. It's just the bare template, which is given by QSPICE. So let's get started. First, we need to detect the rising edge on the ticks signal, and this will be our time base for the counter. So therefore, I will write, we will need another variable, which will be int last tick. Initialize it as 0, and then to detect it goes like the following: last tick at 0, and the tick needs to be 1, and this would give us a rising edge if in the end we put last tick equals tick. Now let's program the counter. Therefore, we'll put if counter bigger than counter max. So when we reach the maximum, we want to reset it to 0. So we put counter equals 0. And if this is not the case, we want to add 1 to the counter. Counter plus plus. So that's for the counter. Now we'll program the PWM. This goes quite simple, because if the input duty cycle, or the desired duty cycle, is bigger than the value of the counter, our PWM should be 1, and if it's below, then we want it to be 0. And that would be everything for now. So I save it, compile the DLL successfully, and I can run the simulation. We will not use the ticks. So this is the desired duty cycle, and we should get a PWM output, which is changing according to the input duty cycle. Let's see, it's around 50%, and here we are almost at 100%. In a power converter, we don't only need one PWM, we often need 2 PWMs, for example, for driving a synchronous buck converter. Therefore, we need a PWM high and a PWM low. I just added a PWM high and a PWM low, and this one is initialized as an output and Boolean. We'll just have to edit here. And this one is PWM high now. Just to put out a PWM like this is very simple. We want it to be driving complementary. So when our PWM high is high, we want the PWM low to be low, so 0. And when the PWM high is 0, we want the PWM low to be 1. So I save it, run it, and run the simulation. I have the simulation. So we have here the PWM high. I'll add another plane. And here the PWM low. And it's seen, you can see here, that they are driven complementary. So when the PWM high is high, the PWM low is low, and vice versa. For driving switching converters, this is still a problem, and therefore we need some dead time in the transition. And this is the next part I want to do or include in the code. And the dead times is always in a microcontroller defined with ticks. So I will define how long the dead time should be. And therefore I will just define the dead time ticks equals 3 in this case. And I need some dead time counter. And the dead time counter will count up to 3 and then again down to 0. For including the dead time, we want, if the duty is higher than the counter and the PWM low goes low, we want to wait 3 ticks until the PWM high goes high. So this will be our dead time. So therefore we need if our dead time counter is bigger than dead time, I called it dead time ticks, bigger than equal dead time ticks. Then we put the PWM 1, PWM high to 1. And if not, we'll put the dead time count, we'll increment the dead time counter by 1. So that's it for this part. And now we need the same. When the PWM high goes low, we want to wait 3 ticks until the PWM L goes high. We can almost insert the same code before we count it up to 3, and then we just leave it at 3 once this one is turned on. And in this else, we count it down to 0. Now this should be everything for the dead time. We will save it, run it successfully, and we can run the simulation. Here we have the simulation. Let's pick some PWM here, put one here, and here it is visible that we have included a dead time here of 3 ticks. And as well on the rising edge for the PWM high as well, we have included the same dead time. This easy to incorporate C++ code is perfect for digital control. In addition, in the previous video, I showed how to do an ADC. So there we have already some basic peripherals we need for a digital control algorithm. That's everything I have for you today on simulating a PWM using QSPICE with C++. Thank you.